Hello and welcome to the Daily Space for today, Monday, August 3rd, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Today's science is the kind of reassuring reality matches expectation science that sometimes we need on a Monday. There are lots of never observed theories in astronomy that we think must be true because there's really no other good way to make the math and the models work. But we don't know. We haven't seen it. For instance, consider white dwarf stars. These tiny objects are the last stage of life for all but the largest stars. They are typically somewhere around the physical size of the moon and have masses from a few tenths of a solar mass out to a little larger than the sun. These stars don't have any nuclear burning in their cores and are supported against gravitational collapse by the ability of electrons to push out against each other, like so many springs between particles. The thing is, this electron degeneracy pressure can only do so much to support a dead star. And just like springs will compact when put under increasing force, these stars will compact. They'll shrink in diameter as increasing mass causes them to crush in on themselves under their own gravity. This weird white dwarf stars should be smaller in radius as they increase in mass phenomena is such an accepted idea that calculating how the radius changes is a standard homework problem for quantum mechanics students. Thing is, we hadn't really been able to observe this theory because it's really hard to see objects the size of the moon at any sort of a large distance. Sure, we can see the light of these white dwarfs, but that hasn't been enough to measure their radii until now. In a new paper in the Astrophysical Journal with first author Vedant Chandra, researchers describe how they used data from the Sloan Digital Sky Survey and Gaia to detail out the observed parameters of more than 3,000 stars to get at their radii through a trick of relativity. Light emerging from high gravity environments gets shifted in color, an effect called gravitational redshifting. Smaller stars with greater mass will exert a larger gravitational pull on light than lower mass, larger white dwarfs. This means that the gravitational redshifting of light is directly related to a star's mass to radius ratio. Well, this may sound almost straightforward. It gets tricky because stars are moving for a whole lot of reasons. And all those motions also shift the light in ways that have to be compensated for. Trying to subtract out motions due to orbits in binary systems, orbits around the galaxy, and so many other possible motions is not always possible. Instead, this team with their more than 3,000 stars used statistics, and they assumed that on average, all the stars have the same random distribution of motions. And if you average all the stars of one radius and all the stars of another radius, those two populations should have the same average motions. Using this logic, they sorted stars by radius using other techniques to get at that radius, and then looked at the mass to radius ratio as a function of radius. Lo and behold, our theories prove true, and at least one thing in our reality is exactly as it should be. But on this particular Monday, it actually wasn't just one thing that was as it should be. In another study appearing in the Astrophysical Journal, this time with first author P. Kagan, researchers using the Atacama Large Millimeter Array have for the first time detected hints of a neutron star in the heart of supernova 1987A. This 33-year-old expanding nebula is still small and dense, And it's hard to see anything through the gas and dust that makes up this beautiful structure. When the supernova went off, neutrinos were detected, indicating that the remnant in the supernova was most likely a neutron star. Despite many attempts to observe that young hot neutron star, it hadn't been seen. And some astronomers were starting to think that maybe something caused that should be a neutron star remnant to collapse into a black hole. Well, it turns out we just weren't patient enough. In these new images from the Atacama Large Millimeter Array, a blob of light shines indistinctly through the nebula in a way that is consistent with a young neutron star heating material in the remnant. According to Danny Page, in spite of the supreme complexity of a supernova explosion and the extreme conditions reigning in the interior of a neutron star, the detection of a warm blob of dust is a confirmation of several predictions. It will be several more years, or maybe even decades, before the remnant expands and thins enough that we can get a good look at this object. But for now, spotting a warm blob in the supernova 1987A nebula is enough to make us all feel that the universe is behaving according to plan. Science can be comforting when things just work. You look at your data, you run math, and boom, things are predicted that you can verify. One extremely satisfying experiment that is currently taking place in Australia is the Desert Fireball Network. In this program, individuals throughout the outback have cameras pointed at the sky looking for meteors streaking through the night. When multiple cameras catch the same streak, it can become possible to calculate where the meteorite fragments may be located and to work backwards and calculate the orbit the meteoroid was on prior to having its passage blocked by the Earth. Researchers from Curtin University recently went through images, headed out, and were able to recover debris from two separate meteor falls. One that was freshly observed and the other event from November 2019. They recovered a stunning fist-sized 1.1 kilogram meteorite, as well as a smaller 0.3 kilogram meteorite. This ability to see a streak, run the calculations, and go find the specific rocks that fell out of the sky in the vastness of the Australian desert is just pleasing. And sometimes the pleasing science just comes from knowing your software works. Researchers using the National Optical Astronomy Observatory of Japan, the Subaru telescope in Hawaii, have taken amazing wide field images in which they hope to find faint smudges of light from young galaxies. Searching these images by eye is time-consuming and subject to all kinds of human error. So this team has instead trained a neural network to search for the objects they're looking for. In a new paper, again appearing in the Astrophysical Journal, this team, led by Takashi Kojima, describes a new ultra-metal-poor galaxy their software discovered. Cataloged as HSCJ 1631 plus 4426. This system is tiny, with only the mass of 800,000 suns, and it's 430 million light years away. While not at some great cosmological distance, this young galaxy is made of material that is largely left over and unchanged from the earliest times in our universe. It appears to have only 1.6% the heavy element abundance of our sun, and most of the stars in the galaxy have formed very recently. This relatively nearby system is a challenge to observe because of its size, but it can be observed with the largest telescopes in the world, and this data should give us new insights into the formation of galaxies. It's also hoped that as they observe more of the sky, their neural network will be able to uncover more of these smudges of forming galaxies. And that's just pleasing. And that rounds out our news for today. This has been your Daily Space.